Imagine standing at the edge of a river, its currents relentless, never repeating. You dip your hand into the water, feeling the cool rush against your skin. But when you pull it out, the river has already changed. The water that touched your fingers is gone, carried downstream, never to return. This river, ceaseless, irreversible, and infinitely paradoxical, is time. It flows through our lives like a force of nature, shaping civilizations, eroding mountains, and carrying us all toward an unseen horizon. Yet for something so universal, time remains humanity's most elusive companion. It slips through our grasp, defies definition, and taunts us with questions that have haunted philosophers, scientists, and poets for millennia. Tonight, we embark on a journey through 99 theories that dance on the edge of this enigma, blending the rigor of physics, the depth of philosophy, and the wonder of human imagination. We'll explore how time bends, loops, and fractures, how it heals and destroys, and how it might not even exist at all. But let us begin with the first ripple in the river, the paradox of time itself. Time is often described as a river, a metaphor that dates back to ancient thinkers like Heraclitus, who famously declared, "No man ever steps in the same river twice." But what makes this analogy so enduring? Like a river, time appears to flow in one direction, carrying the past irretrievably into the future. Yet, as Einstein revealed through his theory of relativity, this flow is not as straightforward as it seems. Time, he showed, is not a universal constant, but a malleable dimension shaped by gravity and velocity. It speeds up, meanders, and slows down, capable of forming whirlpools and even forking into divergent paths. This duality, the tension between time as a rigid mathematical construct and a fluid subjective experience, lies at the heart of our fascination with it. In the physical realm, time is a measurable quantity governed by atomic clocks and space-time curvature. In the human mind, it is a tapestry of memories, anticipations, and fleeting nows. The philosopher J.M.E. McTaggart argued that time's very existence is paradoxical. If the past, present, and future cannot coexist, how can time be real at all? Yet here we are, bound by its currents, prisoners and pilots of a force we barely understand. The river metaphor also hints at time's irreversibility. Just as you cannot reverse a river's flow, we cannot undo yesterday's choices or reclaim a single second of the past. This one-way direction, the arrow of time, is rooted in the second law of thermodynamics, which states that entropy, disorder, in a closed system always increases. Eggs break, stars burn out, wrinkles deepen. But what if this arrow is an illusion? What if, as Einstein suggested, time is a stubbornly persistent illusion, a static block where past, present, and future exist simultaneously? If time is a river, are we mere drifters, carried passively by its currents, or can we learn to navigate its twists and turns? This question threads through every theory we will explore. Consider the paradox of free will. If time is a fixed continuum, as eternalism posits, our choices are pre-written, like actors reciting lines in a cosmic play. Yet our subjective experience insists on agency, the visceral sense that we shape our destinies. How do these perspectives reconcile? The river also symbolizes time's duality as both creator and destroyer. Civilizations rise and fall with the seasons. Love and loss are etched into its banks. The physicist Carlo Rovelli describes time as an emergent property, arising from the interactions of quantum particles and the chaos of entropy. In this view, time is not a fundamental truth, but a story we tell to make sense of change. Yet if time is a story, why does it feel so real? Why does a single moment, a first kiss, a final goodbye, hold such power over us? Even our perception of time's flow is an illusion. Neuroscientists have shown that the present is a fragile construct, stitched together by the brain from sensory input and memory. Like a filmmaker splicing frames, we assemble milliseconds of experience into a seamless narrative. But this narrative is deeply personal. A child's summer stretches endlessly. An adult's year vanishes in a blink. Dopamine, trauma, and novelty warp our internal clocks, making time a subjective tapestry. But what if time itself is an illusion? What if the river we perceive, a linear march from past to future, is merely a shadow cast by deeper, timeless truths? Let's dive into one of physics' most controversial ideas, the block universe theory, where every moment, from the Big Bang to the heat-death of existence, exists eternally, frozen in space-time's unchanging fabric. Einstein's theory of relativity shattered the classical notion of time as a universal ticking clock. Instead, he revealed it as a dimension woven into the fabric of space-time, a four-dimensional tapestry where every event, from the birth of stars to the flicker of a candle, exists eternally. The distinction between past, present, and future, he once wrote, is only a stubbornly persistent illusion. Imagine, then, a universe where your childhood, the present moment, and the death of distant stars are all equally real, frozen in a static block of space-time. This is eternalism. The idea that time does not flow but is a landscape we traverse, like a traveler walking through a pre-written story. To grasp this, picture a book. Each page represents a moment in time. The first page is the Big Bang, the last, the heat-death of the cosmos. As you read, the narrative unfolds, but the pages themselves are unchanging. Eternalism argues that our perception of now is merely the page we're reading. The story is already complete. This theory, rooted in Einstein's equations, suggests that time's arrow, the sensation of moving from past to future, is a trick of consciousness, not a fundamental truth. Eternalism stands in stark contrast to presentism, the belief that only the present moment is real. Under eternalism, the past is not gone, and the future is not unborn. They coexist with the present in a fixed structure. Physicist Hermann Minkowski, who formalized space-time geometry, argued that events are points in this four-dimensional continuum, their relationships governed by relativity. For instance, two observers moving at different velocities might disagree on the order of events, yet both perspectives are valid. A phenomenon known as the relativity of simultaneity. This framework resolves paradoxes like the twin paradox, where one twin traveling at near light speed ages slower than their earthbound sibling. From the traveler's perspective, their timeline is compressed, but in the block universe, both paths are equally real, simply different slices of the same space-time loaf. Eternalism also aligns with quantum mechanics' many worlds interpretation, where every quantum event branches into parallel timelines. But here, instead of branching, all possibilities exist simultaneously, frozen in spacetime's immutable fabric. The clash with human intuition is profound. We feel time's passage acutely, the sting of loss, the thrill of anticipation. Yet eternalism reduces these sensations to illusions generated by our brains. Neuroscientists posit that the present is a 3-second window stitched from memory and prediction, a fragile illusion that masks time's true nature. Philosophers like J.M.E. McTaggart argued that time's supposed flow creates contradictions. If past, present, and future cannot coexist, time itself is unreal. Eternalism sidesteps this by treating time as a dimension, much like space, where all moments are equally valid. If eternalism is true, free will becomes a cosmic paradox. Every decision you've made, every breath you'll take, is etched into space-time's block. This raises unsettling questions. Are we mere actors reciting pre-written lines? If the future is as fixed as the past, does choice matter? The philosopher Baruch Spinoza once wrote that free will is an illusion born of ignorance. The universe, he argued, is a deterministic machine. Eternalism amplifies this, suggesting that our sense of agency is a narrative spun by the brain to make sense of static events. Yet eternalism also offers strange comforts. Grief, for instance, might lose its edge if we view loved ones not as gone, but as existing in another space-time coordinate. Similarly, existential dread about death softens. Your life's final moment is no more real than your first breath. They both occupy fixed points in the block. This perspective aligns with Nietzsche's concept of eternal recurrence, though Nietzsche framed it as a test of amor fati, love of fate. While eternalism presents it as a physical reality, the theory also reshapes ethics. If all actions are preordained, can we assign moral blame? Or does responsibility dissolve in the face of inevitability? These questions echo through philosophy and theology, challenging the foundations of justice and accountability. Even physics grapples with this. The Bootstrap Paradox, where information or objects loop endlessly through time, e.g., a time traveler giving Beethoven's compositions to Beethoven himself, creates causality loops with no origin. In eternalism, such loops are not flaws, but features, a testament to time's timeless nature. But eternalism's serene determinism collides with one of time's most infamous puzzles, the Grandfather Paradox. If you could travel back and erase your own existence, how would that alter the block universe? Would space-time unravel? Or does the paradox reveal a deeper truth about predestination? Let's unravel this tangled thread, where cause and effect twist into a Mobius strip of possibility. Time travel has long been a playground for the imagination, but lurking within its possibilities is a question that strikes at the heart of causality. What if you journeyed back in time and prevented your grandparents from meeting? If you succeed, your parent would never be born, nor would you. But if you were never born, who traveled back to stop them? This is the Grandfather Paradox, a logical knot that has fascinated scientists and storytellers alike. It exposes a rift in our understanding of time, challenging the very idea of cause and effect. The paradox is more than a clever riddle. It forces us to confront the fragility of existence and the rules that govern reality. If time is a river, as we explored earlier, the Grandfather Paradox is a whirlpool, a destabilizing force that threatens to unravel the currents of history. Yet, like all paradoxes, it is a mirror. It reflects our assumptions about free will, destiny, and the nature of time itself. The Grandfather Paradox arises from the possibility of retrocausality, events in the future influencing the past. In its classic form, it imagines a time traveler whose actions negate their own existence. This creates a contradiction. The traveler cannot exist to perform the action if the action succeeds. Such paradoxes are not mere philosophical curiosities. They expose tensions in theoretical physics. For instance, Einstein's equations allow for closed time-like curves, CTCs. paths through space-time that loop back to their origin, theoretically enabling time travel. But if CTCs exist, how does the universe resolve paradoxes? Physicists and philosophers have proposed solutions. One is the Novikov self-consistency principle, which asserts that any actions taken in the past were always part of history. If you tried to kill your grandfather, you would inevitably fail. A slipped knife, a sudden hesitation, because the timeline is self-healing. Another solution invokes the many worlds interpretation of quantum mechanics. Here, traveling back in time branches the universe into parallel timelines. You might erase your existence in one branch, but your original timeline remains intact. These theories share a common thread. They attempt to preserve logical consistency. The universe, it seems, abhors a paradox. As physicist Igor Novikov argued, events on a CTC are self-adjusting to ensure they align with the laws of physics. This aligns with the Bootstrap Paradox, where information or objects loop endlessly through time with no origin, a concept explored in stories like Terminator, where Skynet's creation is triggered by its future self. Both paradoxes challenge linear causality, suggesting time is a tapestry woven with loops rather than a straight line. The grandfather paradox forces us to ask, is time travel inherently impossible, or does the universe enforce rules to prevent contradictions? If the latter, what does this say about free will? If every action in the past is preordained to avoid paradoxes, our choices, even those made in other eras, are scripted. This echoes the block universe theory, where all events exist eternally and time's flow is an illusion. But the implications stretch beyond physics. Imagine a world where time travel is possible but tightly regulated. Would time police emerge to prevent paradoxes as depicted in Ray Bradbury's A Sound of Thunder? Or would the universe itself act as an enforcer, collapsing timelines that threaten consistency? These scenarios blur the line between science and metaphysics. Theologians might see the hand of fate. Scientists, the inevitability of quantum decoherence. The paradox also raises ethical questions. If you could alter the past, would you? The weight of responsibility would be crushing. As philosopher David Lewis noted, time travel would make moral agents of us all, for every act could ripple through eternity. Even small changes, saving a life, uttering a word, might cascade into unrecognizable futures. Yet the grandfather paradox is not just about constraints. It invites wonder. What if, instead of fearing contradictions, we embrace the idea that time is a mosaic of possibilities? The many worlds interpretation suggests that every decision spawns a new universe, rendering paradoxes moot. In this view, the traveler's grandfather might belong to a different branch of reality, preserving the traveler's existence while allowing infinite alternate histories. The grandfather paradox leaves us suspended between possibility and impossibility, a reflection of time's dual nature as both rigid and fluid. But time's tricks are not confined to hypotheticals. Even without time machines, the universe plays with temporality in ways that defy intuition. Consider time dilation, a phenomenon Einstein described as nature's way of keeping everything from happening at once. How does this warping of seconds and years reshape our understanding of existence? Let's explore the science of clocks, gravity, and the relativity of now. Einstein's theory of relativity revealed a universe far stranger than Newton's clockwork model. Imagine two twins. One remains on Earth, while the other rockets into space at near light speed. When the traveler returns, they are younger than their sibling, a phenomenon called time dilation. This isn't science fiction. astronauts aboard the International Space Station age microseconds less than those on Earth due to their orbital velocity. Time, once thought absolute, bends like light through a prism, warped by gravity and motion. But how does this happen? And what does it mean for our understanding of now? To grasp this, picture time as a river again. But this time, its currents are shaped by mass and energy. A clock near a black hole ticks slower than one in empty space, just as a watch at sea level lags behind one atop Mount Everest. These distortions are not quirks but fundamental truths. Time is malleable, a fabric woven with space into the tapestry of space-time. Time dilation arises from two pillars of relativity, velocity and gravity. The faster you move, the slower time flows relative to a stationary observer, a prediction confirmed by experiments. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial jets. The clocks, sensitive to nanoseconds, returned slightly out of sync with ground-based ones, validating Einstein's equations. Similarly, GPS satellites must account for time dilation. Without corrections, their signals would drift by kilometers daily, rendering navigation systems useless. Gravitational time dilation, meanwhile, stems from space-time curvature. Massive objects like Earth or neutron stars warp the geometry of space-time, slowing time in their vicinity. A clock on Mount Everest, farther from Earth's center, ticks faster than one at sea level, where gravity's pull is stronger. This effect scales. Near a black hole's event horizon, time crawls to a near halt, relative to distant observers. These phenomena are not mere abstractions. They reveal a universe where time is relative, dependent on your speed and position in a gravitational field. As physicist Kip Thorne wrote, "Time is personal, varying for each observer." Yet this relativity clashes with our intuition. We perceive time as a universal metronome, a shared rhythm. How can it be both flexible and fundamental? The implications of time dilation are profound, challenging our grasp of reality. If time flows differently for observers in relative motion, is there a universal now? Einstein's relativity of simultaneity suggests not. Two events deemed simultaneous by one observer might appear sequential to another, depending on their relative motion. This erodes the notion of a single, objective present. Consider the block universe theory, where past, present, and future coexist as a static space-time block. In this view, time dilation is a geometric effect. Different observers slice the block at angles, perceiving distinct nows. But if all moments are equally real, how do we reconcile this with our experience of time's flow? Philosopher Henri Bergson argued that subjective time, the duration we feel, is distinct from scientific time, a tension that persists today. Time dilation also raises practical questions. As humanity ventures into space, astronauts on Mars or interstellar missions would experience time differently than Earth. A Martian colony, subjected to weaker gravity and longer orbits, might develop a divergent sense of time. Could this fragment human civilization into isolated temporal frames? The philosophical stakes are equally high. If time is relative, does free will exist? If every now is just a coordinate in space-time, our choices might be illusions, a static script in the block universe. Yet quantum mechanics introduces indeterminacy, suggesting randomness at the subatomic level. How do these frameworks reconcile? Physicist Carlo Rovelli proposes that time emerges from quantum entanglement, a perspective that sidesteps classical paradoxes. Time's malleability is awe-inspiring, but what if it is also cyclical? The Bootstrap Paradox, a loop where cause and effect intertwine, suggests that time might not just bend, but fold into itself. Imagine a notebook sent back in time, its knowledge inspiring the very theory that created it. How does such a loop redefine creation and agency? Let's unravel this enigma, where time becomes a serpent eating its own tail. Imagine waking to find a letter on your desk, its edges worn, the ink faint. The message is unmistakable. Instructions from your future self, detailing a pivotal decision you must make today. But there's a catch. The letter insists you must send it back in time after following its advice. Who wrote it? When did the information originate? The paradox deepens when you realize the letter's existence depends on you obeying it, and later sending it back to yourself. This is the Bootstrap Paradox, a temporal loop where cause and effect are entangled and origins vanish into the haze of eternity. The term bootstrap derives from the phrase pulling oneself up by one's bootstraps, an impossible feat, much like explaining how a time-traveling object or idea exists without a creator. The paradox challenges our linear understanding of time, suggesting that some events are self-sufficient, looping endlessly without a beginning or end. It's a concept that has fascinated storytellers and scientists alike, from the plot of Terminator, where Skynet's creation is triggered by its future self, to theoretical physics models exploring closed time-like curves, CTCs. The Bootstrap Paradox occurs when an object, information, or event is trapped in a causal loop. Unlike the Grandfather Paradox, which creates contradictions, the Bootstrap Paradox is self-consistent, yet unsettling. Consider the letter. If you follow its instructions and later send it back, the letter has no first author. It exists purely because the loop sustains it. Similarly, imagine a time traveler who gives Beethoven a composition, only to discover later that Beethoven was never the original composer. The piece came from the traveler. Physicist Igor Novikov's self-consistency principle suggests such loops are possible under general relativity, provided they adhere to physical laws. In this framework, the universe corrects paradoxes by ensuring that any time travel action was always part of history. The Bootstrap Paradox, then, is not a flaw, but a feature of a universe where time is a closed loop. Quantum mechanics adds another layer. In the many worlds interpretation, the loop might branch into parallel timelines, preserving consistency within each universe. The paradox isn't limited to theoretical physics. It surfaces in mathematics, philosophy, and even art. The Fibonacci sequence, for instance, could be seen as a bootstrap-like pattern, each number derived from predecessors, yet the sequence itself has no origin in a temporal sense. Similarly, myths and religious texts often reference self-fulfilling prophecies, where a prediction's fulfillment ensures its own existence. The Bootstrap Paradox forces us to reconsider creativity and originality. If ideas can loop infinitely without creation, does true innovation exist? Or are we merely recycling concepts from a timeless pool? This question resonates in art and science. Consider Shakespeare's works. If a time traveler gave him his own plays, would they lose their genius? Or does the act of transmission itself constitute creativity? Philosophically, the paradox undermines the notion of free will. If the letter's instructions are inevitable, if you must send it back to sustain the loop, your choices are predetermined. This aligns with the block universe theory, where all events are eternally fixed. Yet the Bootstrap Paradox adds a twist. Your actions in the future directly shape your past, blurring the line between creator and creation. The implications extend to technology and ethics. If a scientist receives a groundbreaking formula from the future, their discovery is actually a message from a loop. Does credit belong to them, the future sender, or the loop itself? This dilemma echoes debates over artificial intelligence, where machines trained on human data generate art or literature indistinguishable from human work. Is it original, or a bootstrap-like echo of existing ideas? Even language is not immune. Words and grammar evolve over time, but their meanings are sustained by loops of usage. A child learns dog from adults, who learned it from prior generations, a bootstrap system with no first utterance. Break the chain, and the concept unravels. The Bootstrap Paradox hints at time's cyclical nature, but what if this cyclicity governs not just objects or ideas, but all of history? Nietzsche's concept of eternal recurrence proposes that every event, every joy and tragedy, repeats infinitely. If the bootstrap loop is a microcosm, eternal recurrence is the macrocosm, a universe where time is not a line, but a circle. Let's explore whether we're doomed to relive our lives endlessly, or if the idea itself is a paradox. In the shadow of the Alps, Friedrich Nietzsche penned a question that would haunt philosophy for centuries. What if every moment of your life, every joy, every regret, every heartbeat, were destined to repeat infinitely? This is the doctrine of eternal recurrence, the idea that time is not a line, but a circle, spinning ceaselessly through identical iterations of existence. Nietzsche framed it as a test of existential courage. Would you at that moment weigh the balance and wish for nothing more fervently than this ultimate eternal confirmation and seal? If the universe is finite, he argued, quantum states must eventually repeat, forcing history to cycle like a cosmic playlist on repeat. But could you endure it? Or would the weight of infinity crush you? Eternal recurrence is both a philosophical provocation and a scientific hypothesis. Nietzsche's concept emerged from his rejection of religious eschatology and linear time. He demanded humans embrace life's totality, flaws and all, as if it were a sacred duty to love fate, amor fati. Yet modern physics hints at a mathematical plausibility. In a finite universe with bounded entropy, quantum fluctuations could reset the cosmos, replaying the same configurations endlessly. Like shuffling a deck of cards infinitely, every possible arrangement, including your life, must recur. This idea intersects with the block universe theory, where past, present, and future coexist eternally. If space-time is static, Nietzsche's loop becomes a geometric truth. Your birth and death are fixed coordinates, repeated infinitely in a closed manifold. The Bootstrap Paradox, too, mirrors eternal recurrence on a microscale, a single event looping forever, unmoored from origin. Both concepts challenge causality, suggesting that time's flow is an illusion and that existence is a mosaic of recurring instants. The emotional weight of eternal recurrence is staggering. If every choice is eternal, does meaning lie in acceptance or rebellion? Nietzsche urged affirmation, to will one's suffering as necessary, to live as though you'd live forever. Yet the paradox of suffering arises. If agony is temporary in a single cycle, its infinite repetition becomes a cosmic injustice. Would a loving universe condemn beings to endless pain? Or does recurrence render suffering moot, a fleeting note in an infinite symphony? Philosophers have split on this. Albert Camus, rejecting eternal recurrence, argued that life's absurdity demands rebellion against meaningless repetition. Existentialists like Sartre might see recurrence as a prison, stripping agency from human action. Conversely, Stoics could embrace it as proof of cosmic order, a reminder to focus on what we control, since the rest is predetermined. Science offers no solace. If quantum states repeat, your consciousness would reset with each cycle, unaware of prior iterations. Would you awaken anew each time? Or is you a transient flicker in an infinite loop? The physicist Sean Carroll notes that even in an eternal universe, entropy's rise might prevent true recurrence as systems trend toward disorder. Yet if time is a dimension, as relativity suggests, perhaps the loops are embedded in spacetime's fabric, unchanging and eternal. Eternal recurrence invites us to ponder infinity's embrace. But what if time itself is a mirage? What if the loops we imagine are merely shadows cast by a deeper, timeless reality? Let's float into the next theory, where time dissolves into illusion, a construct of the mind, not the cosmos. Physicist Carlo Rovelli once likened time to a flickering candle in a dark room, visible only through its effects, yet intangible in essence. Time is not a dimension, he argues, but an emergent property of entropy, a measure of change, not a container for it. This radical idea strips time of its sovereignty, reducing it to a byproduct of the universe's relentless march toward disorder. If Rovelli is right, then time is not a river we drift through, but a shadow cast by the dance of particles. Without change, there is no time. Only a static being, a universe frozen in a single, eternal now. But how can this be? Our lives are governed by clocks, seasons, and the irreversible decay of our bodies. We mourn the past, dread the future, and cling to the present as if it were a lifeboat. Yet Rovelli's vision challenges this. What if time is not a fundamental truth, but a story we tell to make sense of chaos? A hallucination woven by neurons, as fleeting as a mirage in a desert. To understand time's illusory nature, we must descend to the quantum realm, where the familiar rules of physics dissolve. At this scale, particles exist in superpositions, states of probability unmoored from temporal order. There is no before or after in quantum mechanics. Events are entangled across space-time, defying linear causality. Time, as we experience it, emerges only when we zoom out, when trillions of particles interact in thermodynamic systems. Entropy, the tendency of systems to move from order to disorder, is the architect of time's arrow. A shattered vase will not reassemble itself. A scrambled egg will not return to its shell. These irreversible processes create the illusion of time's flow. Rovelli compares this to a flock of birds. Individually, each bird moves chaotically, but collectively, the flock forms a coherent shape. Similarly, time arises from the collective behavior of particles, not from any intrinsic property of the universe. This view aligns with the thermal time hypothesis, which posits that time is a statistical artifact of quantum systems. Just as temperature emerges from the motion of molecules, time emerges from quantum entanglement and entropy. In this framework, the present is not a universal truth, but a localized agreement, a shared delusion among observers in the same thermodynamic frame. If time is an illusion, the implications are staggering. Consider death. If the flow of time is a construct, does death truly end us? Or are we eternal in a timeless reality? This question intersects with the quantum immortality hypothesis, which suggests that consciousness might persist in branches of the multiverse where survival is possible. If time is not linear, death could be a subjective transition between states rather than an absolute cessation. Philosophically, this challenges our grasp of identity. If every moment exists eternally in a block universe, are we infinite beings experiencing slices of a static whole? Or are we ephemeral flickers, deceived by entropy's shadow? The poet William Blake wrote, "Eternity is in love with the productions of time. But Ravelli's vision inverts this. Time is in love with the illusion of eternity. The ethical stakes are equally profound. If time is a human invention, does it strip life of meaning or amplify it? Nietzsche's amor fati, love of fate, takes on new weight, embracing each moment as both transient and eternal, a paradoxical unity. Conversely, the Buddhist concept of anicca, impermanence, aligns with the idea that suffering arises from clinging to time's illusions. Time's illusion invites us to ponder the mind's role in shaping reality. If time is a story we tell, how does the brain weave this narrative? How do neurons stitch milliseconds into a coherent now? And why does a childhood summer feel endless while adulthood vanishes in a blink? Let's explore the neuroscience of time perception, a labyrinth where memory, dopamine, and chaos collide. Why does time fly when you're having fun? Childhood summers sprawl like endless golden afternoons, while adulthood compresses years into fleeting blinks. This paradox of temporal perception is a dance between biology and memory, a reminder that time is not just measured by clocks, but felt in the marrow. Why does joy accelerate the hours while boredom drags them? The answer lies in the brain's alchemy, a cocktail of dopamine, novelty, and the stories we tell ourselves about the past. Consider two moments: the first day of school, vivid and sprawling, and the 10th anniversary of a routine job, dissolved into a haze. Subjectively, these experiences occupy different scales of time, yet objectively, they unfold within the same space-time framework. This dissonance hints at a deeper truth. Time is not just out there, but shaped by the mind. It is a river whose currents we ourselves help steer. The brain is a relentless editor, stitching milliseconds into a coherent narrative. Neuroscientists identify two systems governing time perception: the prospective, how we experience time as it passes, and the retrospective, how we remember it. When engrossed in a novel task, say learning to surf, the brain floods with dopamine, sharpening focus and distorting the now into a blur of motion. Hours vanish, not because time accelerates, but because attention narrows, filtering out distractions. Conversely, trauma or awe hijacks this system. During a car crash, the amygdala, a brain region tied to fear, activates, etching hyper-detailed memories into the hippocampus. Later, these dense neural imprints create the illusion that the event lasted longer, a phenomenon called time expansion. Similarly, awe-inspiring experiences, a sunrise over the Grand Canyon, slow subjective time by saturating the senses, forcing the brain to process more data per second. Routine, however, numbs the clock. A commute repeated daily becomes a mental autopilot, with few novel details to anchor memory. Days collapse into weeks, a effect magnified by adulthood's predictability. As psychologist William James noted, the days, the months, the years of adulthood seem to fly faster as we grow older. If time perception is malleable, can we hack it to live longer? The answer lies at the intersection of neuroscience and philosophy. Practices like mindfulness, rooted in observing the present, may dilate subjective time by flooding the brain with sensory data, mimicking novelty. Travel, learning, and art disrupt routines, creating mental anchors that stretch memory's tapestry. Conversely, the Mandela effect, a collective misremembering of events, e.g., Nelson Mandela's death date, hints at how societal narratives warp temporal perception. If false memories alter our timeline, does shared fiction redefine reality? Yet the pursuit of longer time risks futility. As physicist Carlo Rovelli argues, time's flow is an illusion. Any attempt to manage it battles a phantom. The key may lie in acceptance, savoring fleeting joys and embracing life's ephemerality. Nietzsche's amor fati, love of fate, resonates here, a call to cherish each moment, whether it feels infinite or transient. The brain's manipulation of waking time is profound, but it pales beside the distortions of dreams. In REM sleep, minutes stretch into lifetimes and logic dissolves. How does the dreaming mind sculpt time? And what does this reveal about consciousness itself? Let's drift into the paradox of dreamtime, a realm where seconds become decades and the laws of physics unravel. A lifetime in a nap. In the theater of the mind, dreams unfold like films without directors. A fleeting nap might span decades in a dream world, lifetimes lived, civilizations risen and fallen, all within the span of a REM cycle. How does the brain, unshackled from the laws of physics, warp time so drastically? This is the paradox of dreamtime, where minutes stretch into eons and logic dissolves into poetry. Consider the dreamer who lives an entire lifetime in a single night, childhood adventures, loves won and lost, the slow decay of age, all compressed into a neural symphony. Upon waking, the dream lingers, its temporal distortions leaving a haunting question. If the mind can invent such vivid timelines, what does this reveal about the nature of time itself? Dreamtime's elasticity stems from the brain's nocturnal rebellion. During REM sleep, the prefrontal cortex, the region governing logic, planning, and time perception, goes offline. Without its constraints, the default mode network, DMN, takes over, weaving narratives from memories, emotions, and random neural firings. This network, active during daydreaming and introspection, operates without the timekeeper of the prefrontal cortex, allowing stories to unfold unmoored from chronology. Neuroscientists compare this to a film editor splicing scenes out of sequence. The hippocampus, which consolidates memories, struggles to anchor events in time, creating the jumbled timelines of dreams. A dreamer might traverse decades in seconds because the brain lacks the cognitive machinery to timestamp experiences. Meanwhile, the amygdala floods the system with emotion, etching intense moments into memory, a phenomenon that explains why dream time feels so vast yet so fleeting. Studies using EEG and fMRI scans reveal that during REM sleep, brain activity mirrors wakefulness in regions tied to storytelling, like the DMN, but diverges in areas governing self-awareness and linear time. This dissonance allows a minute of real time to stretch into a subjective hour, as the brain processes stimuli in overdrive, unburdened by the need for coherence. The implications of dreamtime are as profound as they are unsettling. If the brain can simulate lifetimes in minutes, could lucid dreaming, a state of awareness within dreams, grant subjective immortality? Some lucid dreamers claim to pause or extend pleasant experiences, manipulating dreamtime at will. This raises a philosophical quandary. Is consciousness bound by linear time, or can it transcend physical limits? The physicist David Bohm once proposed that consciousness exists in an implicate order, a realm where time is nonlinear and all moments coexist. Dreams in this view offer a glimpse into this hidden dimension, a place where past, present, and future intertwine. If true, dreamtime might not distort reality, but reveal its deeper structure. Fringe theories even link dreamtime to phenomena like the Mandela effect, where collective false memories, e.g. misremembering Nelson Mandela's death date, are attributed to shifts in reality. While these ideas lack empirical support, they echo ancient myths of shared dream worlds, such as the Australian Aboriginal concept of the Dreamtime, a timeless realm underpinning existence. Yet, the science remains grounded. Psychologists attribute the Mandela effect to confabulation, the brain's tendency to fill gaps in memory with fabricated details. Similarly, Dreamtime's distortions arise from the brain's storytelling machinery, not alternate realities. Still, the parallels invite wonder. What if our most vivid dreams are rehearsals for eternity? Dreamtime blurs the line between illusion and reality. But what if the cosmos itself is a dream? The Fermi Paradox, the silence of the universe despite its vastness, forces us to confront another temporal mystery. Where is everyone? If civilizations rise and fall across billions of years, why do we detect no trace of them? Let's explore this chilling question, where time's scale meets existential awe. Where is everyone? The universe is 13.8 billion years old, a vast ocean of stars and planets stretching beyond comprehension. Our galaxy alone harbors billions of Earth-like worlds, many older than our solar system by epochs. Yet when we point our telescopes into the dark, we find only silence. No signals, no ruins, no traces of alien civilizations, just the cold hum of emptiness. This is the Fermi Paradox, a question that has haunted humanity since physicist Enrico Fermi famously asked, "Where is everybody?" The discrepancy between the probability of extraterrestrial life and the utter lack of evidence for it is one of science's most profound mysteries, a cosmic riddle that forces us to confront our place in the universe. The paradox arises from a clash of logic and observation. Given the age and scale of the cosmos, even if intelligent life is rare, it should have had ample time to colonize the galaxy. Calculations like the Drake equation suggest thousands of communicative civilizations might exist in the Milky Way. Yet decades of SETI, search for extraterrestrial intelligence, scans have yielded nothing but static. This silence has birthed theories ranging from the grim to the transcendent. The most haunting solution is the Great Filter, a catastrophic barrier that prevents life from advancing to interstellar communication. This filter could lie in our past, e.g. abiogenesis is extraordinarily rare, or our future, e.g. advanced civilizations inevitably destroy themselves. If the filter is ahead of us, humanity's survival is uncertain. If it's behind us, we might be among the universe's first sentient beings. Other hypotheses propose that alien life exists but remains undetectable. They might use technologies beyond our understanding. Quantum communication. Exist in forms we cannot recognize. Post-biological consciousness, or intentionally avoid contact. The zoo hypothesis suggests advanced civilizations observe humanity in isolation, like scientists studying a primitive species. Alternatively, the dark forest theory, popularized by Liu Cixin's three-body problem, posits that civilizations hide to avoid annihilation by hostile aliens. The Fermi Paradox is a mirror reflecting humanity's existential anxieties. If the Great Filter lies ahead, it warns of self-destruction, nuclear war, climate collapse, or rogue AI. This casts a shadow over technological progress. Are we racing toward transcendence or oblivion? Conversely, if we are among the firstborn civilizations, the universe becomes a blank canvas, pregnant with potential. The paradox also reshapes our cosmic identity. If life is rare, Earth is not just a pale blue dot, but a cosmic miracle, a sanctuary of complexity in a sterile void. This view aligns with the rare Earth hypothesis, which argues that Earth's unique conditions, a stable star, plate tectonics, a large moon, make complex life exceptional. Yet this solipsism clashes with the Copernican principle, which holds that Earth is not special. Philosophically, the silence challenges our narrative of significance. As astronomer Carl Sagan noted, in a universe brimming with life, absence of evidence is not evidence of absence, but it is eerie. The void invites humility. Perhaps intelligence is a fleeting spark doomed to fade, or maybe, as physicist Brian Cox suggests, advanced civilizations outgrow physical expansion, transcending into virtual realities, or merging with the fabric of space-time. The Fermi Paradox leaves us suspended between hope and despair, a reflection of humanity's fragility and ambition. Yet, the universe itself is not eternal. In its final act, stars will fade, black holes evaporate, and time may lose meaning. This is the heat death of the cosmos, a future where entropy reigns and silence becomes absolute. Let's confront this terminal horizon where the paradox of existence meets the inevitability of dissolution. The universe's inevitable whisper. In the farthest reaches of time, beyond the death of stars and the evaporation of black holes, lies a fate as inevitable as it is incomprehensible. Imagine a universe where every proton has decayed, every photon has faded, and all that remains is a lifeless void, uniform and eternal. This is the heat death of the cosmos, a state of maximum entropy where energy gradients vanish and change itself ceases. Yet here lies the paradox. If time requires change to exist, what happens when the universe reaches this terminal equilibrium? Does time dissolve into nothingness, or does it stretch infinitely, a hollow dimension devoid of meaning? The concept is haunting in its finality. In 100 years, a number so vast it dwarfs the age of the universe itself, the cosmos will enter a twilight era. Galaxies will unravel, matter will dissolve into radiation, and even black holes, the universe's longest-lived structures, will emit their last Hawking radiation and blink out. What remains is a sea of photons and leptons, forever drifting apart, never interacting, a realm where time, if it exists at all, has no purpose. This equilibrium is a paradox because time, as we understand it, relies on change. The physicist Ludwig Boltzmann once envisioned a universe where entropy fluctuates locally, creating temporary pockets of order, a gas cloud condensing into a star, for instance. But in heat death, even these fluctuations cease. Without change, the very concept of time becomes ambiguous. If no events occur, does time pass? Or does it freeze, a dimension without substance? Theoretical physicist Sean Carroll argues that in such a state, time loses its directional arrow. Without entropy's rise, there's no distinction between past and future, he writes. Yet the equations of general relativity suggest space-time itself persists, even as its contents dissolve. This raises a haunting question. Is time a fundamental property of the universe, or an emergent phenomenon tied to change? The heat-death paradox challenges our understanding of existence itself. If time persists in a lifeless void, is it merely a mathematical abstraction, a coordinate in a static block universe? Or does it require observers to experience its flow? Philosopher Henri Bergson argued that time is inseparable from consciousness. Without minds to perceive duration, time becomes meaningless. In heat death, where no consciousness remains, does time collapse into a timeless, eternal now? The paradox also intersects with quantum mechanics. The Copenhagen interpretation posits that particles exist in superpositions until observed. If no observers remain in heat death, does the universe revert to a quantum haze of uncollapsed possibilities? Or, as the many worlds interpretation suggests, does every quantum event spawn parallel timelines, each hurtling toward their own heat death? These theories hint at a multiverse where entropy's end is not a conclusion, but a branching infinity of endings. Ethically, heat death casts a shadow over human ambition. If all achievements, art, science, love, are destined to dissolve, what meaning can we assign to existence? Nietzsche's Eternal Recurrence offers a counterpoint. Even in futility, we must embrace life's beauty. Conversely, the physicist Freeman Dyson proposed that life might adapt to survive indefinitely in a cooling universe, hibernating between rare energy transfers. Yet these ideas are speculative comforts in the face of cosmic oblivion. Heat death paints a bleak portrait of the universe's fate, but what if reality itself is an illusion, a simulation flickering on a cosmic screen? If time, entropy, and even consciousness are programmed constructs, the heat-death paradox becomes a line of code in a grander design. Let's question whether the universe is a simulation and what that would mean for time, free will, and our place within the machine. Are we living in a programmed timeline? Elon Musk once remarked that the odds we're not living in a simulation are 1 in billions. His words echo a radical idea. Our reality, every star, every heartbeat, every second that ticks by, might be a line of code in an advanced civilization's experiment. If true, time itself could be a variable, adjusted by unseen programmers. They might rewind epochs, pause centuries, or delete timelines as easily as editing a document. But how does this hypothesis hold up under scrutiny? And what does it mean for our understanding of existence? Imagine a universe where the laws of physics are no more rigid than the rules of a video game. The Big Bang could be a startup sequence, the cosmic microwave background a loading screen, and dark energy a subroutine maintaining the simulation's stability. This is the simulation hypothesis, a theory that blurs the line between science fiction and cutting-edge philosophy. The simulation hypothesis posits that our reality is an artificial construct, a hyper-advanced version of virtual worlds like the Matrix or Westworld. Philosopher Nick Bostrom formalized this in his 2003 trilemma. Either civilizations never reach the technological maturity to run ancestor simulations, they choose not to, or we are almost certainly living in a simulation. Supporters cite eerie coincidences, the universe's mathematical elegance, the pixel-like Planck length, the smallest measurable unit, and quantum mechanics' observer effect, where particles behave differently when measured, a glitch in the code. Even the accelerating expansion of the universe, driven by dark energy, mirrors a simulation's need for computational efficiency. As the cosmos expands, matter thins, reducing the processing power required to simulate it. Advanced civilizations might run simulations for historical research, entertainment, or existential experiments. Each simulation could host billions of conscious beings unaware of their artificiality. If even one civilization creates such simulations, their number could vastly outnumber base realities, making our odds of being simulated near certain. The hypothesis unravels profound questions. If time is programmed, could glitches like déjà vu or the Mandela effect, collective misremembering of events, be code errors? Some theorists suggest these phenomena are rendering hiccups as the simulation recalibrates. Similarly, quantum indeterminacy, the randomness of particle behavior, might reflect the simulator's use of probabilistic algorithms to save resources. Free will becomes a paradox. If our choices are pre-computed, Are we NPCs, non-player characters, in a scripted narrative? Or does the simulation grant emergent consciousness, allowing genuine agency within coded boundaries? Philosopher David Chalmers argues that even in a simulation, consciousness could be real if the program replicates the physical processes generating it. Ethically, the hypothesis is a minefield. If our suffering is a simulation, does it matter? Could the programmers intervene, preventing wars, erasing pain, or are we lab rats in a cosmic experiment? Theologians might reinterpret gods as programmers and prayer as a plea to adjust the code. The theory also faces critiques. Physicist Sabine Hossenfelder notes that simulating a universe would require processing power exceeding the simulated universe itself, a logical impossibility. Others argue that the hypothesis is unfalsifiable, placing it outside scientific inquiry. Yet as quantum computing advances, even skeptics concede that future generations may test the idea, perhaps by searching for signatures of finite computational resources in particle interactions. The simulation hypothesis forces us to question reality's fabric. But what if time's flow is not a programmer's trick, but an illusion of the mind? What if the now we cling to is a flicker in a timeless void, and consciousness itself is the architect of temporality? Let's dive into the paradox of perception, where the present moment is both illusion and anchor. The elusive present. The present moment is a phantom, a flicker of sensation that vanishes as soon as it arrives. Neuroscientists describe it as a 3-second window, stitched together from the echoes of the past and the whispers of the future. But if the now is merely a collage of memory and anticipation, what does it mean to exist in the present? Is it a fleeting illusion, a sliver of time we can never grasp, or the only reality we truly inhabit? This paradox, the tension between the present as a tangible instant and an ephemeral construct, lies at the heart of our experience of time. Imagine dipping a cup into a river. The water you catch is never the same as the water that flowed a moment before. Similarly, the now is a transient convergence of neural processes, a snapshot assembled by the brain to navigate the chaos of existence. Yet this snapshot feels real, urgent, and immediate. How does the mind conjure this illusion, and why does it dominate our consciousness? The brain is a master storyteller, weaving the present from fragments of the past and future. Neurological studies reveal that the now is constructed in 2 phases. The anticipatory brain predicts sensory input milliseconds before it occurs, while the retrospective brain stitches these predictions into a coherent narrative. For example, when you catch a ball, your motor cortex predicts its trajectory before your eyes confirm it. A dance of prediction and correction that creates the illusion of a seamless present. This process mirrors the Bootstrap Paradox, where cause and effect intertwine in a loop. Just as a time traveler might teach Einstein relativity, only to learn it was his idea all along, the brain retroactively shapes the present using future expectations. The hippocampus, which consolidates memories, and the prefrontal cortex, which simulates outcomes, collaborate to frame the now as a bridge between what was and what might be. Yet, this construction is fragile. Experiments show that disrupting neural feedback loops, even briefly, can distort the perception of time. In one study, participants exposed to unpredictable stimuli reported the present as elongated or compressed, suggesting that the brain's timekeeper is easily fooled. The now paradox forces us to question the nature of consciousness itself. If the present is a simulation, is mindfulness a practice of anchoring oneself in the here and now, a glimpse of true reality? or another layer of the illusion. Philosophers like Henri Bergson argued that the true present is durée, a continuous flow of qualitative experience beyond quantification. Yet this durée is inaccessible to the rational mind, which slices time into discrete moments. The paradox also intersects with free will. If the now is shaped by unconscious predictions, are our choices preordained by neural algorithms? Or does the act of becoming aware of the present, a metacognitive loop, grant agency? This echoes the Bootstrap Paradox's infinite loops, where the observer becomes both creator and witness of their reality. Even language reflects the now paradox. The word present derives from the Latin presens, being at hand. Yet its meaning slips through our grasp. Linguist Roman Jacobson noted that tense markers in grammar are humanity's attempt to pin down the ineffable. The now paradox invites us to peer beyond the veil of perception. But what if time itself fractures at the quantum level? In the realm of subatomic particles, past, present, and future might not merely blur. They could dissolve entirely. Let's enter the quantum realm, where superposition and entanglement rewrite the rules of existence, and the now becomes a kaleidoscope of possibilities. Living forever in parallel timelines. Imagine standing at the edge of a cliff, wind tearing at your clothes, heart pounding. You leap not into the void, but into a paradox. In one universe, you plummet. In another, a gust lifts you safely to a ledge. In yet another, you grow wings and soar. This is the promise and terror of quantum immortality. The idea that within the infinite branches of the many worlds interpretation, MWI, every possible outcome of your life unfolds, including your survival of every accident, illness, and catastrophe. Death becomes a statistical impossibility, not because you are invincible, but because some version of you always escapes it. But what does eternity in a fractal of timelines mean for identity, morality, or the soul? The many worlds interpretation, first proposed by Hugh Everett in 1957, posits that every quantum event spawns branching universes, each realizing a different outcome. A photon's path, a decaying atom, a neuron's firing, each splits reality into diverging paths. Applied to human experience, this means that every decision, accident, or random event creates alternate selves. In some branches, you win the lottery. In others, you never buy the ticket. Crucially, in at least one branch, you survive every near-death experience. Quantum immortality emerges as a thought experiment. If consciousness is bound to the branches where survival occurs, subjective experience might persist indefinitely. Physicist Bryce DeWitt famously summarized this: "No one ever dies in their own branch. They simply die in others." This relies on the assumption that consciousness cannot perceive its own termination, a controversial premise. The mathematics of MWI support this. For any lethal event, there exists a non-zero probability of survival, e.g., a stray air molecule altering a bullet's path. As timelines proliferate, the cumulative probability of some version of you surviving approaches certainty. Over time, your conscious experience would thread through the survival branches, creating the illusion of immortality. The implications are as unsettling as they are profound. If quantum immortality is real, death is not an end, but a divergence. Every tragedy you evade in one timeline becomes a horror you endure in another. This raises ethical quandaries. Is it just to prioritize one branch's survival over another's suffering? If countless versions of you suffer eternally in failed branches, does your immortality become a curse? Philosophically, the theory challenges notions of self. Which timeline's you is the real one? If every branch is equally valid, identity dissolves into a swarm of probabilistic selves. This echoes the ship of Theseus paradox. If every component of you is replaced across timelines, what remains constant? The emotional weight is equally stark. Would eternal life in a single branch feel like a gift, or would it become a prison of diminishing novelty? Nietzsche's Eternal Recurrence, the idea of reliving life endlessly, takes on new meaning here, not as a cosmic loop, but as infinite variations of existence, each with its own burdens and joys. Critics argue quantum immortality is a logical stretch. The MWI does not inherently privilege consciousness. Survival in one branch does not negate death in others. Physicist Sabine Hossenfelder notes that MWI's branches are decoherent and non-interacting, making subjective immortality untestable. Yet, the idea persists, a testament to humanity's obsession with cheating death. Quantum immortality paints a dizzying portrait of existence, but what if the universe itself is a fleeting flicker? The Fermi Paradox, the silence of the cosmos despite its vastness, forces us to confront another haunting question. If life is inevitable, why do we detect no trace of it? Let's explore this mystery, where quantum branches meet cosmic loneliness. Are we the last generation? Imagine a cosmic lottery. Each human who has ever lived draws a ticket numbered in the order of their birth. If you hold ticket number 100 billion, what are the odds that the total number of tickets, past, present, and future, is astronomically higher? This is the crux of the Doomsday Argument, a probabilistic warning that humanity's end may be closer than we dare to think. Proposed by astrophysicist Brandon Carter and philosopher John Leslie, the argument uses Bayesian reasoning to suggest that if only 100 billion humans have existed so far, the likelihood of many trillions more is vanishingly small. We might not just be a random blip in history, we could be the final act. At its core, the Doomsday Argument relies on the self-sampling assumption, which treats your existence as a random sample from all humans ever born. If we assume there will be a total of n humans, and you are the nth person, currently 100 billion, Bayesian probability suggests n is unlikely to be in the first 1% or last 1% of all humans. For example, if you are the 100 billionth person, there's a 95% chance humanity's total population n falls between 1.05 trillion if you're in the first 5% and 1.05 trillion if you're in the last 95%. This implies a high probability of near-term extinction. The argument's power lies in its simplicity. It sidesteps specifics about technology, climate, or war, focusing solely on your birth order. Physicist J. Richard Gott III applied similar logic to predict the Berlin Wall's fall, arguing that if something has existed for time Te, it's likely to persist for another T3 to 3 Ti. For humanity's 200,000-year existence, this suggests a lifespan between 6,000 and 6 million years, a window that, if closing, leaves little room for complacency. Yet the Doomsday Argument is fiercely debated. Critics highlight the reference class problem. Should humans include only anatomically modern Homo sapiens, or extend to future post-humans or AI? Changing the reference class alters the probability. Others invoke the self-indication assumption, which posits that you should reason as if you're a random sample from all possible observers, favoring scenarios where n is large. Under SIA, discovering you're the 100 billionth human doesn't update the odds. Your existence is unsurprising in a thriving future. The Doomsday Argument forces a collision between rationality and emotion. If the math is correct, optimism becomes a form of denial. Yet, as philosopher Nick Bostrom notes, even a small probability of a vast future can outweigh the doomsday conclusion. For instance, if there's a 1% chance humanity survives for 1 trillion years, the expected number of future humans, 10 billion, still dwarfs our past. This tension mirrors debates over the Mandela effect, where collective false memories, e.g. misremembering Nelson Mandela's death date, are sometimes attributed to quantum shifts between timelines. If reality is a multiverse, as suggested in Saud, the Doomsday Argument's grim prediction applies only to our branch, a single thread in an infinite tapestry. Survival in other timelines could render the argument moot. Ethically, the Doomsday Argument challenges our responsibility. If extinction is probable, should we prioritize present hedonism or desperate efforts to avert disaster? Climate scientist James Hansen warned that the Doomsday Argument is a call to action, not despair. Conversely, critics argue it's a statistical trick, conflating epistemology, what we can know, with ontology, what is. As physicist Sean Carroll writes, probability is a tool for reasoning, not a feature of the universe. The paradox also intersects with art and myth. Mary Shelley's The Last Man, 1826, envisioned humanity's extinction via plague, a narrative reflection of the doomsday dread. Today, the argument haunts Silicon Valley's transhumanists, who see escaping Earth or uploading minds as routes to beat the odds, the weight of infinite lives. Friedrich Nietzsche's Eternal Recurrence is a philosophical sledgehammer. What if every moment of your life, every joy, every heartbreak, every mundane breath, were destined to repeat infinitely? This is not a metaphor, but a demand. Nietzsche challenges us to confront whether we would embrace this eternal repetition with gratitude, amor fati, love of fate, or crumble under its crushing weight. The idea transcends physics, striking at the core of human purpose. If time is a loop, are we heroic actors in an endless play, or Sisyphus forever pushing his boulder? Eternal Recurrence posits that time is not linear but cyclical, a Mobius strip of existence. In an infinite universe with finite configurations of matter and energy, quantum states must eventually repeat, forcing history to cycle identically. Nietzsche's vision is visceral. The universe is a fire that consumes and reconstitutes itself eternally, with no creator to assign meaning. Each iteration is identical. Your choices, triumphs, and regrets are not singular, but infinite. This aligns with the block universe theory, where past, present, and future coexist as a static space-time block. Yet Nietzsche's recurrence is not passive. It is a call to action. To say yes to life, to affirm every moment, even suffering, is to transcend nihilism. Conversely, to reject recurrence is to succumb to despair, clinging to the illusion of linear progress. Nietzsche's amor fati offers a path to peace, but critics argue it borders on existential surrender. Philosopher Albert Camus rejected eternal recurrence, framing life's absurdity as a reason to rebel, not acquiesce. The tension mirrors debates over the Mandela effect, where collective false memories, e.g. misremembering Nelson Mandela's death date, hint at alternate timelines. If reality itself is fluid, does recurrence become a form of collective delusion, or a glimpse of the loop's mechanics? Scientifically, eternal recurrence intersects with the heat-death paradox. If the universe reaches maximum entropy, could quantum fluctuations reset it, sparking a new cycle? Physicist Sean Carroll notes that in a truly infinite cosmos, such fluctuations are inevitable, though staggeringly rare. This aligns with the Big Bounce theory, where big bangs and crunches cycle eternally. Ethically, recurrence challenges morality. If every action repeats infinitely, does virtue lose meaning? Nietzsche argues the opposite. Only by embracing recurrence can we live authentically, unburdened by regret or fantasy. Yet this raises a haunting question. If a murderer's crimes recur endlessly, does justice exist? Or is morality merely a product of temporal perspective? Eternal Recurrence insists time is a circle. But what if it's a myth? What if the flow of time is an illusion, a construct of consciousness rather than physics? Let's dissect the block universe theory, where past, present, and future are frozen in space-time. A tapestry of moments, not a river. A frozen tapestry of moments. Physicists envision the universe not as a flowing river, but as a vast, frozen tapestry. A block universe where every moment, from the Big Bang to the heat death of existence, is etched into space-time's fabric. Imagine a film reel containing every frame of history, unspooling not sequentially, but simultaneously. Your birth, first love, and death exist as fixed coordinates, as permanent as mountains in a landscape. This is the block universe, a timeless continuum where time's flow is an illusion, a mental construct projected by consciousness onto an unchanging reality. Einstein's theory of relativity laid the groundwork for this view. In his equations, time is a fourth dimension, interwoven with space into a single geometric entity, space-time. Events are not transient, but permanent fixtures in this continuum. For instance, a supernova exploding in 1054 CE, observed as the Crab Nebula, and you're reading these words are both static points in the block, their pastness or presentness dependent on the observer's vantage. This challenges Newton's notion of absolute time. In the block universe, there is no universal now. Two observers moving at different velocities might disagree on whether a star died or a civilization rose first, yet both perspectives are valid. This relativity of simultaneity implies that time's flow is subjective, a byproduct of how consciousness navigates the block. As physicist Paul Davies writes, "We are like spectators in a cinema." The block universe also resolves paradoxes like the twin paradox. The traveler's slower aging isn't a bend in time, but a difference in their path through spacetime's geometry. Similarly, quantum mechanics' many worlds interpretation aligns with the block's static nature. Every outcome of a quantum event exists as a branch in the universal wave function, frozen in the continuum. If all moments are equally real, grief and fear lose their urgency. Why mourn a loved one's death if their existence in the past is as permanent as your present? Philosopher Arthur Schopenhauer argued that sorrow arises from clinging to transient illusions. In the block universe, acceptance, amor fati, becomes rational. Resistance to fate is futile when every joy and tragedy is eternally fixed. Yet quantum theory introduces tension. The quantum theory of time posits that time's flow arises from fundamental symmetry violations, suggesting dynamics are not purely deterministic. If true, the block universe's rigidity is an approximation, a static snapshot of a universe still being written. This aligns with experiments showing quantum systems resist being frozen, their behavior probabilistic rather than fixed. The theory also reshapes ethics. If actions are preordained, moral responsibility becomes ambiguous. Nietzsche's Eternal Recurrence, embracing infinite repetition, offers a solution. Live as if every choice matters infinitely. Conversely, the block universe's determinism could justify nihilism, rendering morality a human fiction. The block universe frames time as a frozen sculpture, but our minds perceive it as a flowing river. How does consciousness carve now from the block's eternity? What neural mechanisms create the illusion of motion in a static cosmos? Let's explore the neuroscience of time perception, a labyrinth where memory, prediction, and emotion collide. How does the brain stitch time? Your brain is a master weaver, threading milliseconds of sensory data into a seamless tapestry of now. Close your eyes and recall the scent of rain on pavement, the sound of a loved one's laughter, the warmth of sunlight on your skin. These fragments, scattered across neural networks, are fused into a unified moment, a process so effortless it feels like magic. Yet this magic is a profound scientific mystery, the temporal binding problem. How does the brain synchronize sights, sounds, and sensations, separated by milliseconds, into a coherent present? And what does this reveal about the nature of consciousness itself? The temporal binding problem arises from a fundamental contradiction. Sensory signals reach the brain at different speeds. Visual data processes in 150 milliseconds, while auditory signals arrive in just 8–10 milliseconds. Yet, we perceive reality as instantaneous, a symphony of synchronized input. Neuroscientists posit that the brain acts as a timekeeper, compensating for delays through predictive processing. For example, when you clap your hands, your motor cortex predicts the timing of the sound, aligning it with the tactile feedback. This prediction and correction loop creates the illusion of simultaneity. At the neural level, synchronization occurs through phase locking and oscillatory coherence. Groups of neurons fire in rhythmic patterns, gamma waves, theta waves, to bind disparate signals. The hippocampus, critical for memory, sequences events into narratives, while the prefrontal cortex integrates them into the now. This process mirrors the block universe theory, where time's flow is an illusion, a static tapestry of moments stitched together by the brain. Quantum mechanics adds another layer. Some theories suggest that consciousness itself arises from quantum coherence in microtubules within neurons, enabling non-local temporal binding. While controversial, this idea aligns with experiments showing that quantum effects influence neural processes. If time perception is rooted in quantum biology, could AI ever replicate it? Current neural networks process time sequentially, excelling at pattern recognition but lacking the brain's fluidity. For instance, AI can predict the next frame in a video, but cannot feel the passage of time as humans do. This gap hints at a deeper truth. Temporal binding may rely on biological processes, emotion, memory, and embodiment that resist digitization. Ethically, this raises unsettling questions. If neuroscientists decode the brain's time-stitching algorithms, could they manipulate perception? Imagine propaganda that distorts temporal sequences, making events seem simultaneous or reversing cause and effect. In a block universe where all moments coexist, such manipulation might exploit the brain's reliance on predictive frameworks. The stakes are existential. Philosopher David Hume argued that causality itself is a mental construct, a habit of thought. If the brain's binding mechanisms are hacked, our grasp of reality unravels. This mirrors the Mandela effect, where collective false memories suggest a malleable timeline. The brain's ability to bind time is both a marvel and a vulnerability. But what if this power is weaponized? Could temporal manipulation become a tool for control, eroding free will or rewriting history? Let's enter the realm of ethics, where the science of time perception collides with moral responsibility. The morality of time travel. Time travel is not merely a scientific curiosity, it is a moral minefield. Imagine standing at the edge of a temporal precipice, faced with choices that could erase genocides, resurrect extinct species, or prevent personal tragedies. But each intervention risks cascading consequences, from erasing loved ones to unraveling civilization itself. This is the realm of temporal ethics, where philosophers grapple with questions once confined to myth. Should we alter the past to create a better future? Or does tampering with history make us tyrants, playing God with lives we cannot comprehend? As historian George Washington once wrote, "The foundations of our national policy rest on the basis of futurity, a principle that echoes through time, demanding we weigh progress against preservation." Temporal ethics sits at the intersection of philosophy, physics, and chaos theory. At its core lies a tension between two imperatives: historical fidelity and moral urgency. Philosopher David Lewis argued that time travelers are guests of the past, bound by the same ethical duties as historians, to observe, not interfere. Others, like utilitarian thinkers, advocate for interventions that maximize well-being across timelines, even if it means rewriting history. The debate mirrors real-world dilemmas. Consider the eradication of smallpox, a medical triumph that saved millions but also erased a virus from existence, altering ecological and evolutionary trajectories. Temporal ethics amplifies this tension. Would extinguishing the 1918 flu pandemic save lives, or rob humanity of scientific advancements spurred by the crisis? Neuroscientists liken temporal decision-making to the brain's temporal binding problem, synthesizing fragmented data into coherent narratives. Just as the brain stitches milliseconds into now, ethicists must integrate scattered consequences into moral judgments. This process is fraught. The butterfly effect, where minor changes cascade unpredictably, suggests even noble intentions could birth dystopias. The implications of temporal ethics are staggering. If we save a single life in the past, are we obligated to save all? Philosopher Mary Midgley warned that moral isolationism, ignoring the past suffering, is indefensible, yet intervention risks paternalism. This paradox is dramatized in Ray Bradbury's A Sound of Thunder, where stepping on a prehistoric butterfly reshapes human language and politics. Temporal ethics also challenges notions of identity. If you prevent your grandparents' meeting, does your non-existence negate the moral weight of your action? This loops back to the quantum immortality paradox. Survival in one timeline does not absolve harm in others. Critics argue that temporal ethics is a luxury of the powerless, a thought experiment until time travel becomes feasible. Yet as AI and quantum computing advance, analogs emerge. Editing CRISPR genes or altering AI training data mirrors temporal intervention, forcing us to ask, when does improvement become erasure? Ethics anchor us to humanity's compass. But what if time itself is a living entity, a conscious force that resists or guides our choices? Indigenous philosophies like the Maori concept of Wakapapa, genealogical ties to all existence, suggest time is not a dimension, but a sentient web. Let's imagine a world where time breathes, watches, and judges. A being whose heartbeat we feel but cannot fathom. The body's clockwork. Your body is a celestial instrument, attuned to rhythms older than humanity. Every cell pulses with a circadian beat, a 24-hour symphony synchronized to the rise and fall of the sun. But what if this internal clockwork is not merely a response to light and darkness, but a resonance with deeper cosmic forces? Lunar cycles that stir tides in your blood, solar flares that tweak your neurotransmitters, or even dark matter whispering through your DNA. Chronobiology, the study of biological time, reveals that we are not just inhabitants of time, but dancers to its hidden melodies. Yet as science unravels these connections, a question emerges. Are we harmonizing with the universe's tempo, or are we deaf to its true rhythm? At the heart of chronobiology lies the circadian rhythm, orchestrated by the suprachiasmatic nucleus, SCN, in the brain, a cluster of 20,000 neurons that act as your body's atomic clock. This master timekeeper responds to light, calibrating hormones like melatonin to regulate sleep, metabolism, and even immune function. But light is not the only conductor. Temperature, meal timing, and social interactions fine-tune peripheral clocks in organs like the liver and heart, creating a symphony of physiological processes. Yet the SCN's dominion is challenged by cosmic forces. Marine organisms, from algae to horseshoe crabs, synchronize their reproductive cycles to lunar phases, a phenomenon called circulunar rhythm. Humans, too, may harbor lunar sensitivity. Studies suggest correlations between menstrual cycles and the moon's phases, though debates rage over causation. Solar activity adds another layer. Solar flares, which bombard Earth with charged particles, have been linked to heart rate variability and serotonin fluctuations. Subtle disruptions that hint at a celestial dialogue. Dark matter, the universe's invisible scaffolding, presents the wildest hypothesis. Some theorists propose that weakly interacting massive particles, WIMPs, could influence biochemical reactions, nudging evolution or aging in ways we've yet to decode. While speculative, this aligns with chronobiology's core insight. Time is not just a backdrop, but a participant in life's drama. If biological clocks are entangled with cosmic rhythms, could aligning with them extend life? Consider the Greenland shark, which lives centuries, its cells ticking in sync with Arctic light cycles. Or the tardigrade, which enters cryptobiosis, suspending its circadian rhythm to survive millennia. These extremorphals suggest that harmony with environmental time, whether earthly or cosmic, may be a longevity strategy, yet chaos looms. Modern life, with artificial light and transcontinental travel, disrupts circadian alignment, contributing to ailments from diabetes to depression. This discord mirrors the temporal binding problem. Just as the brain stitches milliseconds into now, organisms must synchronize trillions of cells to a coherent rhythm. Failures in this process, like jet lag or shift work disorder, reveal the fragility of our temporal harmony. Philosophically, chronobiology challenges anthropocentrism. Indigenous cultures like the Maori view time as a living web, taiao, where human cycles are inseparable from lunar phases and seasonal stars. Modern science echoes this. The SCN's light dependency ties us to the sun's nuclear furnace 93 million miles away. We are stardust animated by cosmic rhythms, a humbling thought. Chronobiology reveals time as a language written in light, hormones, and celestial pulses. But what if this language has a syntax, a hidden structure that orders events, memories, and possibilities? Let's decode time's grammar, where physics, philosophy, and poetry converge to ask, is time a narrative we author, or a story we're bound to repeat? Time travel's perfect loop. Imagine standing at the edge of a river, its currents carving a path through stone over millennia. You throw a boulder into the water, hoping to redirect its flow, but the river swallows the stone, adjusting its course imperceptibly. Still a river, still itself. This is the essence of the Novikov self-consistency principle, a theory that reimagines time travel not as a tool to rewrite history, but as a thread woven seamlessly into the fabric of the past. Proposed by physicist Igor Novikov in the 1980s, the principle asserts that any action taken by a time traveler in the past was always part of history. There are no paradoxes, only loops, events that enforce their own existence, like a serpent swallowing its tail. Novikov's principle emerged as a solution to the grandfather paradox, which asks, what happens if you go back in time and kill your grandfather, preventing your own birth? Novikov's answer is elegant. You cannot. The universe, he argued, resists contradictions by ensuring that time travel actions are self-consistent. If you journey to the past, your presence there is not an intrusion, but an integral part of the timeline. Every decision, every accident, is folded into the original history like a puzzle piece. This principle aligns with Einstein's block universe theory, where past, present, and future coexist as a static continuum. Time travel, in this view, is not a disruption, but a recognition of pre-existing connections. For example, in the film Terminator, the machines send Skynet's components back in time, inadvertently sparking the creation of the technology that leads to their own rise. The loop closes, the timeline holds. Novikov's work draws on quantum mechanics, particularly the many worlds interpretation, but diverges by rejecting branching timelines. Instead, it posits a single, self-correcting history, where probabilities collapse into a consistent outcome. Experiments simulating closed time-like curves, CTCs, theoretical paths through space-time that loop back to their origin, support this, showing that quantum states adjust to avoid paradoxes. The Novikov principle's most profound implication is its negation of free will. If time travelers cannot alter the past, their choices are preordained, a script written into the universe's structure. This echoes the block universe perspective, where every event is eternally fixed. Yet the principle introduces a twist. Agency is not absent, but constrained by the timeline's geometry. You can choose to act, but the universe will correct deviations, rendering your choices part of the inevitable flow. Consider Harry Potter and the Prisoner of Azkaban. When Hermione uses a time-turner to rescue Sirius, their actions in the past are revealed to have always been part of the story. Their new timeline is the only one that ever existed. Novikov's principle mirrors this narrative device, suggesting that reality itself enforces such loops. Philosophically, this raises questions about destiny and morality. If a time traveler attempts to prevent a tragedy but fails because their attempt caused the tragedy, are they morally responsible? Novikov's framework implies a grim determinism. Ethics are bound to outcomes, not intentions. Yet physicist Sean Carroll argues that the principle's reliance on cosmic censorship, the universe hiding paradoxes, feels like a narrative convenience, not a scientific law. The Novikov principle paints a universe of perfect loops, but what governs the direction of those loops? Why do we remember the past, but not the future? This is the realm of the arrow of time, a mystery as ancient as thermodynamics itself. Let's explore why time's river flows one way and whether its current can ever reverse. Why time flows forward. Time's arrow is a relentless force. Eggs shatter but never reassemble. Candles melt but never reform. We age but never grow younger. This unidirectional flow, from order to disorder, birth to decay, is the universe's most familiar stranger. Yet, why does time march forward? The answer lies in a law as profound as it is inevitable. The second law of thermodynamics, which states that entropy, disorder, in a closed system always increases. But why should a physical law dictate the direction of time itself? And if entropy's rise defines the arrow, could reversing it bend time backward? The arrow of time emerges from the interplay between entropy and probability. Imagine a deck of cards. Shuffled, it transitions from ordered, all suits aligned, to disordered, randomized. The odds of unshuffling it are astronomically low, not because it's impossible, but because there are vastly more disordered states than ordered ones. This asymmetry defines time's direction. The universe, like the cards, began in a low entropy state, the Big Bang, and has been unraveling ever since. Physicist Arthur Eddington coined the term arrow of time in 1927, linking it to entropy's rise. At the quantum level, particles exhibit time symmetry. Processes can run forward or backward without violating laws. Yet in the macroscopic world, entropy's dominance creates an irreversible flow. A dropped wine glass smashes into pieces, each fragment a step toward higher disorder. To reverse this would require not just energy, but a reconfiguration of probability itself. If entropy's rise creates time's arrow, could reversing entropy reverse time? In theory, yes. But the energy required to reorder a single shattered glass exceeds the output of a star. Practically, entropy's arrow is a one-way street. This aligns with the heat-death hypothesis, where the universe reaches maximum disorder and time's flow loses meaning, yet quantum mechanics hints at subtler possibilities. Experiments with closed time-like curves, CTCs, theoretical paths through spacetime that loop back, suggest that quantum systems can self-correct to avoid paradoxes, preserving entropy's arrow. This implies that even at the quantum level, time's direction is fundamental, not a statistical fluke. Philosophically, the arrow of time challenges notions of free will. If the future is a higher entropy state, are our choices preordained by thermodynamics? Or does consciousness, our perception of now, grant a sliver of agency? This tension mirrors the block universe theory, where time's flow is an illusion and entropy's rise is a geometric property of spacetime. Entropy's grip defines our reality, but what if the arrow itself is an illusion? What if time's flow, like the colors of a rainbow, is a construct of perception, a trick of the mind in a universe where past, present, and future coexist? Let's question the nature of time's direction, venturing into a realm where physics and philosophy collide. The unreality of time. Time feels real. It presses on us, relentless and unyielding, shaping our lives with its rhythms. Yet philosopher J.M.E. McTaggart dared to ask, what if time is not a feature of reality, but an illusion, a linguistic trick woven by human perception? In his seminal work, The Nature of Existence, 1927, McTaggart argued that time cannot exist because its very nature, past, present, and future, is inherently contradictory. If time is unreal, what does this mean for existence itself? Are we living in a flickering moment suspended between nothingness and eternity? McTaggart's argument challenges not just physics, but the essence of human experience. Imagine a clock ticking away seconds, marking the passage from one instant to the next. But what is a second, really? Is it now? Was it then? Or will it be later? This paradox lies at the heart of McTaggart's critique. Time's supposed flow is an illusion, and the distinctions we make between past, present, and future are mere constructs of language. McTaggart's argument hinges on two frameworks, the A series and the B series. The A series describes time as dynamic, the ever-changing now that moves from past to future. In this view, events transition from being in the future to being in the present, and finally, to being in the past. This aligns with our subjective experience of time's flow. In contrast, the B series describes time as static, a fixed sequence of events ordered by earlier than and later than relationships. For example, the Battle of Hastings occurred in 1066, earlier than the moon landing in 1969. Here, time is timeless. There is no now, only a permanent timeline where all moments coexist. McTaggart argued that the A series is logically incoherent. If the now exists, it must also have been in the future and will become part of the past. But these states, future, present, and past, are mutually exclusive. An event cannot simultaneously be all three, yet the A series demands this contradiction. Since the A series is fundamental to our notion of time, McTaggart concluded that time itself cannot exist. The B series avoids this contradiction by treating time as a static block, but it fails to account for the dynamic flow we experience. Without the A series, there is no moving now, no sense of progression. This leaves us with a universe frozen in space-time, where time's reality dissolves into an eternal stasis. If time is unreal, why do we perceive it so vividly? Neuroscience offers a clue. The brain stitches milliseconds into a coherent now through processes like predictive coding and memory consolidation. This temporal binding creates the illusion of flow, even though McTaggart's paradox suggests that flow is an impossibility. Philosophically, McTaggart's argument intersects with the block universe theory, where past, present, and future coexist eternally. If time is an illusion, consciousness becomes the architect of temporality, a flicker of awareness in a timeless void. This echoes Buddhist teachings on impermanence, anicca, which posit that the self and time are fleeting constructs. Yet McTaggart's conclusion raises unsettling questions. If time is unreal, is existence itself a mirage? Philosopher Henri Bergson countered that time's qualitative duration, durée, is irreducible, a lived experience beyond logical dissection. For Bergson, McTaggart's paradox misses the point. Time is not a concept to be analyzed, but a felt reality, inseparable from life itself. Ethically, McTaggart's paradox challenges notions of responsibility. If time is unreal, are actions bound by causality, or are they free-floating events in a timeless continuum? This tension mirrors debates over the Mandela effect, where collective false memories suggest malleable timelines. If time lacks objective existence, does morality lose its anchor? McTaggart's paradox invites us to question time's reality, but its cultural impact is undeniable. From ancient calendars to modern clocks, humanity has structured its existence around the rhythm of seconds, minutes, and years. Yet what happens when those rhythms fracture? Let's explore the Mandela effect, a modern mystery where shared memories diverge from recorded history, blurring the line between personal and collective time. Collective false memories. Imagine a world where millions of people share the same vivid memory. Nelson Mandela dying in prison during the 1980s, his tearful funeral broadcast across the globe. Yet reality tells a different story. Mandela lived until 2013, passing away at the age of 95 after decades of activism and leadership. This phenomenon, the Mandela effect, raises profound questions about the nature of memory, time, and reality itself. Are these shared false memories glitches in the timeline, evidence of parallel universes bleeding into our own? Or are they simply collective hallucinations, the result of human psychology's quirks? The Mandela effect is more than a curiosity. It is a window into how we construct reality. If memory can be so profoundly wrong on a mass scale, what does this say about the reliability of our perception of time? And if timelines can diverge or merge, what does this mean for the fabric of existence? The term Mandela effect was coined by paranormal researcher Fiona Broome, who first noticed widespread misremembering of Mandela's death date. Since then, countless examples have emerged. The Berenstain Bears, misremembered as Berenstein, Darth Vader's famous line, "Luke, I am your father," which he never actually says, and even the spelling of popular brands like Fruit Loops, often remembered as Fruit Loops. These discrepancies span cultures, languages, and generations, suggesting something deeper than individual error. Explanations fall into two camps. Psychologists attribute the Mandela effect to confabulation, a process where the brain fills gaps in memory with fabricated details. For instance, hearing about Mandela's imprisonment might lead some to falsely recall his death during that period. Similarly, repeated exposure to misinformation, such as misquoted movie lines or altered logos, can overwrite original memories. On the other hand, proponents of quantum mechanics speculate that the Mandela effect could result from quantum decoherence or shifts between parallel timelines. In this view, small variations in quantum states create alternate realities, and individuals may occasionally slip between them, carrying memories from one timeline into another. While speculative, this hypothesis aligns with the many worlds interpretation, where every decision spawns branching universes. The implications of the Mandela effect are vast, challenging both personal and collective notions of reality. If memories are unreliable, how do we trust our understanding of history, or even the present? Philosopher David Hume argued that causality itself is a mental construct, inferred from patterns rather than observed directly. The Mandela effect amplifies this skepticism. If timelines shift imperceptibly, causality becomes a fragile thread. Ethically, the Mandela effect raises unsettling questions. If reality diverges across timelines, whose version is true? Consider the ethical dilemmas posed by technologies like AI-generated deepfakes, which already blur the line between fact and fiction. If collective memory can be manipulated or fractured, how do we preserve truth in an age of digital malleability? The phenomenon also intersects with neuroscience. Studies show that memory is not static but dynamic, reconstructed each time it is recalled. This reconstruction leaves room for error, especially when influenced by external factors like media narratives or social reinforcement. Yet the sheer scale of the Mandela effect, millions sharing identical false memories, suggests something beyond individual psychology. Could consciousness itself play a role, binding groups into shared temporal frameworks? Philosophically, the Mandela effect echoes McTaggart's paradox. If past, present, and future cannot coexist, perhaps our perception of time is inherently fragmented. Alternate timelines might explain why some remember events differently, as if their consciousness briefly inhabited another branch of the multiverse. The Mandela effect invites us to question the fluidity of time and memory. But what if time itself is not continuous? What if it is quantized, composed of discrete units, like pixels in a digital image? Let's consider the possibility of Chronons, the smallest units of time, and explore whether space-time is a smooth continuum or a pixelated mosaic. The smallest unit of time. Imagine time not as a smooth, continuous river, but as a cascade of tiny droplets, each one an indivisible unit of existence. This is the provocative idea behind Chronons, hypothetical atoms of time proposed by quantum gravity theories. At scales smaller than the eye, or even current instruments, can perceive, time might be granular, composed of discrete moments rather than a seamless flow. These Planck-scale particles, named after physicist Max Planck, who first theorized the smallest units of spacetime, could redefine our understanding of reality itself. Could Chronons resolve ancient paradoxes like Zeno's arrow, which questioned how motion is possible if time is infinitely divisible? And what does this mean for the nature of causality and consciousness? The concept of Chronons arises from attempts to unify quantum mechanics with general relativity, a quest that has eluded physicists for over a century. In classical physics, time is treated as a continuum, flowing smoothly from past to future. However, at the Planck scale, approximately 10^43 seconds, quantum effects dominate, and spacetime may lose its smoothness. Instead of being infinitely divisible, time could consist of discrete quanta, akin to pixels in a digital image or frames in a film reel. Each frame, or chronon, represents the smallest possible increment of time, a fundamental limit beyond which further division becomes meaningless. Quantum gravity models, such as loop quantum gravity, LQG, and string theory, support this idea. LQG posits that spacetime is woven from loops of quantized geometry, creating a fabric with inherent granularity. Similarly, string theory suggests that strings vibrating at the Planck scale give rise to both matter and spacetime itself, implying that time might also have a pixelated structure. These theories aim to resolve contradictions between relativity, which treats spacetime as smooth, and quantum mechanics, which describes reality as discrete and probabilistic. Chronons also offer solutions to ancient philosophical puzzles. Zeno's paradoxes, which questioned the possibility of motion by dividing space and time into infinite segments, find resolution in a quantized framework. If time is composed of indivisible units, there is no infinite divisibility, only finite steps between events. This aligns with experimental evidence from quantum systems, where processes occur in discrete jumps rather than continuous flows. The implications of chronons challenge our deepest intuitions about time. If time is pixelated, does it still flow? Or is it a series of static frames stitched together by perception? Neuroscientists suggest that the brain constructs the illusion of continuity by stitching milliseconds into a coherent now. If chronons exist, this process would involve assembling discrete temporal quanta into a seamless narrative, a kind of temporal pixelation that mirrors the block universe theory. Philosophically, chronons blur the line between determinism and free will. If time consists of fixed, indivisible units, every moment might already be etched into the fabric of reality, leaving no room for deviation. Yet quantum indeterminacy introduces randomness at the Planck scale, suggesting that even within a pixelated framework, unpredictability persists. This tension mirrors debates over the Novikov self-consistency principle, which asserts that time travel actions are preordained versus interpretations of quantum mechanics that allow for branching timelines. Ethically, the idea of quantized time raises questions about agency and responsibility. If every decision occurs within a discrete chronon, are we truly choosing or merely following a script written into the space-time lattice? This echoes the existential dilemmas posed by McTaggart's paradox, where time's unreality undermines notions of causality and moral accountability. Scientifically, chronons could revolutionize technology. Understanding the Planck scale might enable breakthroughs in quantum computing, where operations occur at unimaginable speeds. It could also shed light on black holes, whose singularities compress space-time into infinitesimal points, potentially revealing the true nature of chronons. Chronons invite us to reimagine time as a pixelated mosaic, but what if the future influences the past? Retrocausality, The idea that cause and effect can operate in reverse challenges our linear understanding of time. Could Chronons serve as conduits for backward-flowing information, linking distant moments across the space-time lattice? Let's examine the paradoxes and possibilities of retrocausal theories, where the arrow of time bends in unexpected ways. The future shapes the past. Picture this. A ripple in a pond moves outward, but instead of fading into stillness, it reverses course, shaping the stone that caused it. This is the essence of retrocausality, a concept from quantum mechanics where future events appear to influence the past. At first glance, it defies our deepest intuitions about causality, the idea that cause precedes effect. Yet experiments like the delayed choice quantum eraser suggest that time's arrow may not be as rigid as we assume. Could the future reach backward through time, rewriting history at the quantum level? Or is retrocausality merely an illusion born of mathematical abstraction? Retrocausality forces us to reconsider the very fabric of reality. If the future can shape the past, what does this mean for free will, destiny, and the nature of existence itself? Are we passive actors in a cosmic script, or co-creators of a timeline that flows both ways? Retrocausality emerges from the peculiarities of quantum mechanics, particularly phenomena like superposition and entanglement. In the classic double-slit experiment, particles behave as waves when unobserved, but collapse into definite states upon measurement. The delayed choice quantum eraser takes this further. Even after a particle's behavior is recorded, a future choice, whether to observe or erase its path information, seems to retroactively determine whether it acted as a wave or particle. This suggests that time's directionality is not absolute. Physicist John Wheeler, who proposed the delayed choice experiment, likened it to a cosmic U-turn, where the act of observation in the present influences the particle's past trajectory. While some interpret this as evidence of retrocausality, others argue it reflects the probabilistic nature of quantum systems rather than true backward causation. Mathematically, retrocausality aligns with certain interpretations of quantum mechanics, such as the transactional interpretation, which posits that particles exchange handshakes between past and future states. These handshakes create a self-consistent loop, ensuring that effects are always aligned with their causes, even if those causes occur later in time. Similarly, the block universe theory supports retrocausality by treating past, present, and future as coexisting slices of space-time, where causality operates across all temporal dimensions. Critics caution against conflating correlation with causation. Philosopher Hugh Price argues that retrocausality might simply reflect our ignorance of underlying processes, akin to misinterpreting shadows as objects. Others point to decoherence, the process by which quantum systems interact with their environment, as a more plausible explanation for apparent retrocausal effects. Despite these debates, retrocausality remains a tantalizing possibility, challenging the linear flow of time enshrined in classical physics. The implications of retrocausality are profound, reshaping our understanding of fate and agency. If the future can influence the past, does destiny exist at the quantum level? Some interpretations suggest that retrocausality enforces a form of predestination, where outcomes are predetermined by the interplay of past and future events. This echoes the Novikov self-consistency principle, which asserts that time travel actions are integral to history and cannot alter established timelines. Philosophically, retrocausality blurs the line between determinism and randomness. If the future shapes the past, Are our choices truly free, or are they constrained by a web of causal loops spanning both directions in time? This tension mirrors debates over the block universe theory, where time's flow is an illusion and all events coexist eternally. Ethically, retrocausality raises unsettling questions. If actions in the future can rewrite history, how do we assign responsibility for events that seem inevitable? Consider a scenario where a decision made today alters not only tomorrow, but also yesterday's conditions. An existential paradox that challenges notions of moral accountability. Scientifically, retrocausality could explain anomalies like the Mandela effect, where collective memories diverge from recorded history. If timelines shift due to retrocausal influences, shared false memories might result from alternate futures bleeding into the present. While speculative, this hypothesis aligns with quantum theories suggesting that consciousness itself might interact with space-time, creating feedback loops between perception and reality. Retrocausality invites us to imagine a universe where timelines blur and causality bends. But what about personal time? How does the human mind construct its own sense of past, present, and future, weaving moments into a coherent narrative? Let's reflect on the psychology of time, exploring how memory, emotion, and identity shape our inner clocks, and whether they mirror the mysteries of quantum retrocausality. Is only the present real? Close your eyes and take a breath. The past is a memory, the future a dream, but this moment, right now, feels undeniably real. For temporal solipsists, this intuition is not just a fleeting sensation but a profound truth. Only the present exists. The past and future are mere constructs of the mind, illusions spun from perception and imagination. But what does it mean to live in a universe where time is reduced to a single, eternal now? Is this moment all we truly have? Or is it a prison of our own making? Temporal solipsism challenges the block universe theory, which posits that past, present, and future coexist as a static continuum. Instead, it aligns with presentism, the belief that only the current moment has ontological reality. Yet temporal solipsism takes this further, suggesting that even the boundaries of now are subjective, shaped by individual consciousness. If true, this redefines existence itself. Life becomes a solitary dance within the confines of an ever-shifting present. At its core, temporal solipsism rejects the notion of time as an external dimension. Unlike eternalism, which treats space-time as a four-dimensional block where all moments are equally real, temporal solipsism frames time as a purely subjective experience. This view resonates with philosopher Henri Bergson's concept of durée, or lived duration, a fluid, qualitative sense of time that cannot be measured or quantified. For Bergson, the now is not a slice of the timeline, but a continuous flow, inseparable from consciousness itself. Neuroscience lends some support to this perspective. Studies show that the brain constructs the present through a process called temporal binding, stitching milliseconds of sensory input into a coherent moment. This now is not instantaneous, but spans approximately 3 seconds, a window of awareness that bridges past perceptions and future predictions. Beyond this narrow frame, the past dissolves into memory, and the future remains speculative, both existing only as mental constructs. Critics argue that temporal solipsism collapses under scrutiny. If only the present exists, how do we explain causality, memory, or even the scientific method, which relies on consistent temporal relationships? Quantum mechanics complicates matters further. Experiments like the delayed choice quantum eraser suggest that future actions can retroactively influence past events, implying that time structure transcends subjective experience. Yet for temporal solipsists, these phenomena merely highlight the limits of human perception, not the objective reality of time. The implications of temporal solipsism are both liberating and confining. On one hand, it frees us from the weight of the past and the anxiety of the future. If only the present exists, regret and anticipation lose their grip, leaving us free to inhabit the moment fully. This aligns with mindfulness practices, which emphasize non-judgmental awareness of the now as a path to peace and clarity. In this view, temporal solipsism transforms us from prisoners of time into masters of mindfulness, unshackled from the burdens of history and destiny. On the other hand, temporal solipsism risks isolating us within an endless succession of fleeting instants. Without the continuity provided by past and future, identity itself becomes fragmented. Philosopher David Hume argued that the self is nothing more than a bundle of perceptions, each tied to a specific moment in time. If only the present exists, then the self is perpetually reinvented, lacking coherence or permanence. This mirrors the existential dread of McTaggart's paradox, where time's unreality undermines notions of meaning and purpose. Ethically, temporal solipsism raises unsettling questions. If only the present is real, does morality become a matter of immediate consequences rather than long-term responsibility? Consider climate change. If the future is an illusion, why sacrifice present comfort for generations yet to come? This tension echoes debates over the Mandela effect, where collective memories diverge from recorded history, challenging our trust in shared timelines. Scientifically, temporal solipsism clashes with theories like the block universe and quantum retrocausality, both of which imply that time extends beyond subjective experience. Yet proponents argue that these frameworks are mathematical abstractions, unable to capture the lived reality of the now. As physicist Carlo Rovelli writes, time is not a dimension we traverse, but an emergent property of our interactions with the world. Temporal solipsism invites us to embrace the present as the only reality. But what if time is not just a subjective experience, but a dimension we can traverse? Imagine stepping outside the constraints of now, moving freely between past, present, and future like a traveler exploring a vast landscape. Let's imagine the possibilities of time as a navigable dimension, where the boundaries of the present dissolve into infinite horizons. Aging across timelines. Aging across timelines. Imagine two siblings inseparable in childhood, yet destined to live vastly different lives. One remains on Earth, aging through decades of sunrises and seasons, while the other journeys into the cosmos at near light speed, returning younger than their twin. This is the twin paradox, a cornerstone of Einstein's theory of relativity that reveals time's malleability and its cruelty. For the traveler, time slows. For the earthbound sibling, it marches relentlessly forward. What does this mean for human experience? Is interstellar travel a doorway to immortality or a recipe for heartbreak? The twin paradox is not just a thought experiment. It is a profound meditation on the nature of existence. It forces us to confront the fragility of human connection in a universe where time itself is relative. If we can stretch or compress our lifespans through motion, are we masters of time or its prisoners? The twin paradox arises from Einstein's special theory of relativity, which states that time dilates at high velocities. For an astronaut traveling close to the speed of light, clocks aboard their spaceship tick slower relative to those on Earth. Upon returning, they find themselves younger than their twin, who remained in Earth's gravitational field and experienced time at a normal rate. This phenomenon is not speculative, but experimentally verified. In 1971, physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial jets. The results confirmed that time dilation occurs even at everyday speeds, though the effects are negligible compared to near-light-speed travel. Similarly, astronauts aboard the International Space Station age microseconds less than their Earthbound counterparts due to their orbital velocity. The paradox deepens when considering acceleration and deceleration. Critics once argued that the twin paradox contradicts itself because both twins could claim the other is moving relative to them. However, general relativity resolves this by accounting for the traveler's acceleration and deceleration, which break the symmetry of the scenario. Only the twin who undergoes significant changes in velocity experiences time dilation. Mathematically, the effect is described by the Lorentz factor, which quantifies time dilation as a function of velocity. At 90% of light speed, for example, 1 year for the traveler corresponds to over 2 years for the twin on Earth. This disparity grows exponentially as velocity approaches the speed of light, suggesting that extreme relativistic travel could extend lifespans indefinitely, at least from the traveler's perspective. The implications of the twin paradox are both tantalizing and tragic. On one hand, it suggests that interstellar travel could grant a form of immortality. A crew embarking on a mission to Proxima Centauri, 424 light-years away, at 99% of light speed, might return to Earth centuries later, biologically unchanged, while entire civilizations rise and fall in their absence. This aligns with the concept of quantum immortality, where consciousness threads through timelines where survival is possible, yet the human cost is staggering. The traveler's return would be a reunion fraught with alienation. Friends and family would have aged or passed away, leaving the traveler adrift in a world unrecognizable and indifferent. This mirrors the existential dread of McTaggart's paradox, where time's unreality undermines notions of continuity and belonging. Philosophically, the twin paradox challenges our understanding of identity. If the traveler returns younger, are they still the same person? Their memories and experiences diverge so drastically from those of their twin that their shared history becomes a fragile illusion. This tension echoes debates over the Mandela effect, where collective memories diverge from recorded history, challenging our trust in shared timelines. Ethically, the paradox raises questions about sacrifice and responsibility. If humanity ventures into space, who bears the burden of temporal displacement? Should explorers accept the loneliness of extended lifespans for the sake of discovery? Or does this fracture human connection irreparably, leaving travelers as eternal outsiders in their own species? Scientifically, the twin paradox also intersects with quantum mechanics. Experiments like the delayed choice quantum eraser suggest that time's flow is not absolute, raising the possibility that relativistic effects are part of a deeper, non-linear structure. Could the traveler's slowed aging reflect a shift in their interaction with space-time's quantum fabric? While speculative, this hypothesis aligns with theories of Chronons, discrete units of time that might underpin reality itself. The twin paradox reveals time's elasticity, but leaves us questioning its very nature. If time bends under the influence of velocity and gravity, what if it is not a fundamental dimension, but an illusion, a construct of perception and consciousness? Let's conclude our exploration of time by stepping back to ask, Is time a river we drift through, or a story we tell ourselves to make sense of chaos? The myth of now. What is now? Is it a razor-thin slice of space-time, a fleeting moment that exists universally for all observers? Or is it merely a construct of the mind, a subjective flicker in an otherwise seamless continuum? Albert Einstein once remarked, "The distinction between past, present, and future is only a stubbornly persistent illusion." This profound statement challenges our most basic intuitions about time. If relativity complicates simultaneity, undermining the idea of a universal now, then what does this mean for human experience? Are we all adrift in our own private timelines, each with its own elusive present? The ontology of the present forces us to confront the tension between physics and perception. Relativity tells us that now is not absolute, but relative, dependent on one's velocity and position in space-time. Yet subjectively, the present feels immediate, undeniable, a foundation of existence itself. How do we reconcile these perspectives? At the heart of the debate lies Einstein's theory of relativity, which dismantles the notion of a universal now. In a relativistic universe, simultaneity is observer-dependent. Two events deemed simultaneous by one observer may appear sequential to another moving at a different velocity. This undermines the classical Newtonian view of time as an absolute shared dimension. Instead, time becomes a malleable fabric woven into the geometry of space-time, where now is no longer a fixed point, but a fluid concept. Consider two astronauts floating in deep space. If one travels at near light speed while the other remains stationary, their experiences of now diverge dramatically. For the traveler, time slows. For the stationary astronaut, it flows normally. When they reunite, their perceptions of the present will be irreconcilable. This phenomenon, known as relativity of simultaneity, suggests that now is not a shared reality, but a localized experience shaped by one's frame of reference. Quantum mechanics adds another layer of complexity. Experiments like the delayed choice quantum eraser imply that causality itself may not follow a linear timeline, further blurring the boundaries of now. Some interpretations of quantum mechanics suggest that particles exist in superpositions until observed, collapsing into definite states only when measured. If consciousness plays a role in this collapse, as some theories propose, then the present might be a construct of perception rather than an objective feature of the universe. Philosophically, the ontology of the present intersects with debates over eternalism versus presentism. Eternalism, aligned with the block universe theory, posits that past, present, and future coexist as equally real slices of space-time. In this view, now is merely a subjective spotlight moving across a static timeline. Presentism, on the other hand, asserts that only the present moment has ontological reality, with the past fading into memory and the future remaining unwritten. Each framework offers a radically different vision of existence, one timeless and unchanging, the other dynamic and fleeting. The implications of relativity's challenge to simultaneity are profound. If now is observer-dependent, does this mean there is no universal present? Could each individual inhabit their own now, isolated from others by the quirks of space-time? This raises unsettling questions about human connection and shared experience. Imagine two people standing side by side, seemingly sharing the same moment. Relativity suggests that their nows may differ subtly, or even drastically, depending on their relative velocities or positions within Earth's gravitational field. For instance, someone atop Mount Everest experiences time slightly faster than someone at sea level due to weaker gravitational pull. While these differences are imperceptible in everyday life, they underscore the fragility of our assumptions about shared time. Philosophically, the absence of a universal now challenges notions of free will and moral responsibility. If each person's present is unique, how do we assign accountability for actions that occur in overlapping yet distinct timelines? This tension echoes debates over retrocausality, where future events influence past ones, blurring the line between cause and effect. Ethically, the fragmentation of now raises questions about justice and fairness. Consider legal systems built on the assumption of a shared temporal framework. If simultaneity is relative, how do we determine the sequence of events in disputes involving high-speed travel or astronomical distances? This mirrors the ethical dilemmas posed by the twin paradox, where temporal disparities fracture human relationships. Scientifically, the ontology of the present intersects with theories of Chronons, discrete units of time that might underpin reality itself. If time is quantized, then now could represent the smallest measurable unit of existence, a Planck-scale pixel in the space-time lattice. This aligns with loop quantum gravity and string theory, which suggests that space-time has a granular structure at the smallest scales. Yet if now is quantized, does it lose its subjective immediacy, becoming just another mathematical abstraction? Culturally, the myth of now resonates deeply. Indigenous philosophies such as the Maori concept of taiao, the interconnected web of existence, emphasize the fluidity of time, viewing past, present, and future as inseparable threads in a cosmic tapestry. Similarly, Buddhist teachings on impermanence, anicca, reject the notion of a fixed now, framing time as a continuous flow beyond conceptual division. These perspectives offer alternative frameworks for understanding the present, not as a discrete moment, but as a dynamic process. The ontology of the present reveals time's elusiveness, but perhaps the answer lies not in dissecting its nature, but in embracing its mystery. Let us return to where we began, to the river of time, flowing ceaselessly through our lives. Whether an illusion or a fundamental truth, time shapes our stories, binding us to the cosmos and to each other. As we conclude this journey, let us reflect on the beauty and complexity of time, a force both intimate and infinite. Embracing the unknowable. We began this journey with a simple question: what is time? Along the way, we traversed 99 theories, each offering a fragment of insight into time's nature. From the ticking hands of clocks to the infinite loops of eternal recurrence, from the pixelated quanta of Chronons to the fluid flow of lived experience, these ideas form a symphony, a cacophony of notes that sometimes clash, sometimes harmonize, but never fully resolve. Time resists definition, slipping through our fingers like water. And yet in its unknowability lies its beauty. Perhaps the purpose of exploring time is not to solve its mysteries, but to marvel at their dance, to embrace the paradoxes as essential to existence itself. Time is a paradox because it exists simultaneously as a scientific phenomenon and a philosophical enigma. In physics, it is a dimension woven into space-time, governed by equations that describe its dilation, curvature, and quantization. Yet in philosophy, it is an elusive now, a flicker of awareness that defies measurement or categorization. These perspectives are not contradictory, but complementary, each illuminating different facets of the same gemstone. Consider the twin paradox, where time bends under the influence of velocity, leaving one traveler younger than their sibling. This is not just a thought experiment. It reflects the malleability of time at relativistic scales. But what does it mean for human connection, for identity? These questions transcend physics, delving into the realms of ethics, psychology, and even art. Similarly, the Mandela effect blurs the line between memory and reality, challenging our trust in shared timelines. Is it a glitch in perception, or evidence of parallel universes bleeding into our own? These ambiguities remind us that time is not merely a subject of study, but a lived experience, deeply intertwined with our sense of self and meaning. The tension between science and philosophy mirrors the broader human struggle to reconcile certainty with wonder. Science seeks to explain time through equations and experiments, while philosophy embraces its mystery, framing it as a narrative we construct to make sense of chaos. Together they form a dialogue, a conversation without resolution but rich with possibility. What does it mean to live with time's paradoxes? For some, it may be a source of frustration, the unanswerable riddles of existence. For others, it is a call to humility, a reminder that the universe exceeds our capacity to understand it. The Novikov self-consistency principle teaches us that time travel actions are preordained, weaving seamlessly into history. Yet retrocausality suggests that the future can shape the past, bending causality in ways that defy intuition. These competing ideas do not negate each other. Instead, they enrich our understanding, revealing time's complexity as a tapestry of contradictions. Ethically, embracing time's paradoxes invites us to reconsider our relationship with mortality, free will, and responsibility. If the future influences the past, as retrocausality implies, how do we assign accountability for actions that ripple across timelines? If only the present exists, as temporal solipsism argues, does morality become a matter of immediate consequences rather than long-term impact? These questions have no easy answers, but they challenge us to think deeply about what it means to live well, to act with intention, compassion, and curiosity in a world shaped by forces beyond our control. Scientifically, the exploration of time's paradoxes has practical implications. Advances in quantum mechanics and relativity inspire technologies like quantum computing, space travel, and even attempts to manipulate time itself. Yet these innovations also raise ethical dilemmas. Should we pursue immortality through interstellar travel, knowing it might fracture human connection? Can we trust AI systems trained on data influenced by temporal distortions, such as false memories or altered histories? These challenges underscore the importance of balancing innovation with reflection, ensuring that our pursuit of knowledge serves humanity rather than alienates it. Culturally, time's paradoxes resonate across disciplines and traditions. Indigenous philosophies like the Maori concept of taiao view time as a living web, inseparable from relationships with land, ancestors, and community. Buddhist teachings emphasize impermanence, anicca, inviting us to let go of attachment to fixed notions of past, present, and future. These perspectives complement Western scientific frameworks, offering holistic ways to engage with time's mysteries. Perhaps the greatest lesson of this journey is that time cannot, and should not, be reduced to a single explanation. Its paradoxes are not flaws, but features, reflections of a universe too vast and intricate for any one theory to encompass. To explore time is to embrace uncertainty, to find joy in the questions rather than fear in the unknown. Close your eyes. Let the river of time carry you. Feel its currents, its eddies, its silences. The paradoxes will keep until tomorrow.